Hello and welcome. I had a request for a performance example in addition to the one that I've already posted. And so I've prepared a problem that would follow along with Chapter 1 in Hennessy and Patterson on performance. So what we have here today is a question that requests that we calculate the relative performance of two different machines. Now, in a basic problem, you might be given the cycles per instruction, the CPI, for the two different machines. But in this particular problem, it will require us to calculate the average CPI. So in this table here, we have the different types of instructions. Then we have the relative CPIs of each of those types of instructions. And then for a particular compiler mix, we have how many of each type of the instructions are in each of the classes. So the overall task is going to be made up of a mix of different types of instructions, and each of those instructions then have a different cost as it relates to CPI, and of course for the two different machines they're going to be different. So our first question asks us to calculate the CPI, and then the next question asks us to take a look at the relative performance of A and B. And finally, we're asked to calculate the clock rate that would allow the two computers to have equal performance. So before we begin, I'll just remind you that the basic formula in Hennessy and Patterson for the time that it takes to complete a particular task or program is going to be given by the product of three different factors. So the time is always equal to the number of instructions times the CPI times the cycle time. Now the cycle time is going to be in units of time, like seconds. Maybe it's given in nanoseconds or microseconds, but the cycle time is going to be 1 over the frequency. Oftentimes we talk about computers having a certain clock rate, but clock rate is 1 over time, often given in hertz or gigahertz. And then the cycles per instruction imply how many cycles are in each instruction. And the number of instructions, that's going to be the number of instructions per program. So if you actually analyze the units on these, we'll see that number of instructions is going to be the number of instructions per program. And so that'll be in the units will be instructions per program. Cycles per instructions are going to be the cycles per instruction. And then the clock cycle time, we talk about it being in units of time, yes, but that's the number of, that's units of time divided by the cycles. And so this is going to be seconds over cycle here. C-Y-C-L-E. Go ahead and spell that out. So if we look at this, we wanted time. Well, we've got the instructions per program, the cycles per instruction, and the seconds per cycle. We can see the cycles cancel and the instruction cancel. And so at the end, then we have units of time per program. So yeah, the time is usually in seconds, but it's implied for the number of seconds that it takes to run a particular program. All right. Well, here's where it gets kind of difficult. If we want to calculate the time, we need all three of these numbers. But in many cases, we're just looking at comparing the performance of two different machines, two different processors, two different CPUs, however you want to modify it. So computer A, oftentimes it's talking about machine A, or maybe it's processor A, but we're looking at two different design schemes. And so we might not have all three of these numbers, but if we hold a particular characteristic constant, then we still can compare two different architectures, even if we don't have all of these numbers, because if one of these stays the same and we're comparing the relative performance, then they'll be the same, and when we divide the two, then we'll always get then we'll be able to make a comparison. But if we talk about relative performance, then realize that the factor is always going to be the time of the slow divided by the time of the fast. These are supposed to be subscripts here. So the time of the slow divided by the time of the fast. Now, you say, wait a minute, why is the slow in the numerator? Well, the time is going to be greater for a slow computer than for a fast computer. Therefore, we're always going to get a ratio greater or equal to 1 in this case, and that's the format that Hennessy and Patterson asks us to do, because we're always going to come up with a statement that says, and this is the template that you can use, computer or machine, so it's these three blanks that we'd need to fill in at the end to say which one is better and by how much. So this ratio here will always go in the middle blank, and then you just have to remember which one, if it's A or B then A, B then A, then or A then B, then you just have to remember, okay, the fast one is going to have the smaller time, and that you just have to keep track of here. But this ratio here, the time divided by the time, is going to be in the middle here. It'll always be greater or equal to 1 since we're using the numerator-denominator notation this way. And therein lies the kicker. Since we see that at the end we're always going to make a ratio of these, oftentimes the number of instructions will be the same for the two different computers. And if the number of instructions is the same, then that common number of instructions will divide out, and we don't necessarily need to know the number of instructions in an absolute sense. We only need to know that they're the same, because if they're the same, then they'll divide out, and we can still come up with our quantitative metric, even though we might not know the value of the instructions. If the number of instructions is the same, we can still use this ratio, even though we're going to have the time per instruction is what we'd end up with if we don't know the value of the number of instructions. So how do we know when the instructions are the same? It's a couple of telltale signs, and if you look at the problems in the back of Hennessy and Patterson, you'll see most of the ones that they have in the problem set are ones that don't give you necessarily the number of instructions, and they'll say that they're on the same machine, the same compiler. The telltale sign is when you have the same instruction set. So if you have the same instruction set, the implication is that for a given set task, then you will have the same number of instructions. Now, there's one caveat with that. If you have the same instruction set, you also have to have the same compiler. So in this particular problem, we say, well, not only do they have the same instruction set, they have the same compiler. So if you take the same code on the same instruction set with the same compiler, it's going to barf out the same program, even though that program is going to run differently on different architectures. So the compiler is the same, the instruction set's the same, therefore the implication is that the number of instructions is going to be the same for these. So that's the telltale sign. If the compiler is constant, the instruction set is constant, then the number of instructions will be constant as well. All right, so we're faced with this table, and we'd say, well, which one of these CPIs would I use in my overall equation here? I don't know which one. There's so many different CPIs. Well, what we'd have to do is come up with an average CPI. And if we have a bunch of different CPIs, we need to find the average. We'll use the weighted average. So we need to know what the relative frequency of these different types of instructions would be, and then we can come up with an overall CPI. And that's actually the very first part of this question, is come up with the average CPI for A and B. Now that average CPI is going to be heavily dependent on what mix of instructions the compiler spits out. So in this particular case, we have these, but if we would run a different program or a different benchmark, we'd have a different mix, and therefore we'd have a different average CPI. But the problem only asks us for this particular program with this particular output of the compiler. So what we do is we have to have a weighted average with these. So basically for each of these, we're going to find the component of the component contribution of each of these types of instructions for the given machine. we're always going to then multiply the mix times the CPI, and then we're going to add everything. So for example, in this first one, we take the weighted average. Well, we would take 1.5 times 0.25, and that's going to be equal to 0.375. 0.375 in that case. Then we've got 1 times 0.3, and that's going to be equal to 0.3. And then we've got 1 times 10%, and that's going to be equal to 0.1. We've got 4 times 0.25, and that's going to be equal to 1.0. And then we've got 20 times 10%, and that's going to be equal to 2.0. And what do? We have to add these up. We have to add these up in column format, and then we get 3.775 in that case. So we multiply each of the CPIs times the relative frequency to get a constituent component, and then we add up the components to get the overall CPI. So then that would answer this question. What's the overall CPI? It'd be 3.775. CPI for B, I'm not going to write it out, but when we multiply each of these pairwise, we're going to get a 0.25, a 0.45, a 0.12, a 0.5, and a 1.2. We add them all up. So we add them, and then we get 2.52. And that is the answer for the CPI of B. Now, before we barrel along and say, well, A has such a terrible CPI on average, then B must be the faster computer. However, that's not the whole story. What if the computer A was running at twice the clock rate? So it's executing these instructions at a clock rate that's twice as big. So it's a cycle per instruction, but if the cycle time is only half for CPI A, for computer A, then we still might have a better performance. So the clock rate matters, and we cannot stop here to say which one's faster. Now, if the problem said they're at the same clock rate and they have the same number of instructions, then this works. But remember, we have 3 components here, and in this problem, we're only holding the number of instructions constant, and we still have to worry about the cycle time. So we go on to the next question. And the next question teases that concept out. Computer A has a clock cycle time of 0.5 nanoseconds, and computer B is running at 1.8 gigahertz. They're giving us mixed units here. So what we need to do is make sure that we are using the same comparison here. And remember that the fundamental formula uses the cycle time. So here we've got the cycle time of 0.5 nanoseconds. That's in the form that we need to use. And computer B, well, it gives us in gigahertz. That is the number of cycles per second, not the number not the time, the seconds per cycle. So let's go ahead and convert both of those. For computer A, if we wanted to know the frequency, then that's going to be 1 over 0.5 nanoseconds, and that's going to be 2 gigahertz. Now, if we want to get a sanity check, we look and say, oh, okay, now I can compare these two numbers. This is not a 6, it's a G. Compare these two. Oh, yeah, computer A is running a little bit faster. And that's what we usually use when we talk about computers. However, if we want to find the computer B cycle time, then that is going to be equal to 1 over 1.8 times 10 to the 9th hertz. And remember that hertz is 1 over seconds. So if you have 1 over seconds in the denominator, the seconds are going to go back up into the numerator. And when we do the SI conversion, we get 0.556 nanoseconds. And again, now we can compare apples to apples. A has a shorter clock cycle time than B. B has a longer time per cycle than A. So we can compare either the clocks or we can compare the cycle time, but we then we can compare apples to apples in that case. Okay, now our question is which one is faster and by how much? The quantitative statement comparing the two computers. Let's go ahead and write that down so that we know what our ultimate goal is. Remember, there are 3 blanks. So we say computer blank is blank times faster than blank. Now this is going to be the ratio, and we already remember that the number of instructions for both programs, for both architectures, is the same. So we can look at the number of the time per instruction for each of these, and we can compare apples to apples that way. So computer A, if we look at that, we have then a cycle time, 0.5 nanoseconds per cycle. And then we have the CPI that we determined for A, which is 3.775 cycles per instruction. And here we have an overall 1.89 nanoseconds per instruction. Nanoseconds per instruction. Then for B, we have 0.556 nanoseconds and then 2.52 cycles per instruction. And then that's going to be equal to 1.4 nanoseconds per instruction. So if they have the same number of instructions, we're looking at the amount of time per instruction. If they have the same number of instructions, this ratio is going to be the ultimate performance comparison. So now we say which one is slower, which one's faster. I'd much rather have computer B in this case, but the ratio is always the bigger number on top because we want to have a number greater than or equal to 0. In computers, we want the slower time is the better computer. So then we have 1.89 divided by 1.4, and that is going to be equal to 1.35. And we're comparing apples to apples because it's the same number of instructions, and this is what goes in the middle blank. Is 1 times 3 faster. Now we have to go back and we have to check which one was better. A had a greater time or a greater time per instruction than B, so B is going to be faster, and computer B is 1.3 times faster than computer A. And that's the answer there. All right. Now finally it says, wait a minute, what if my competitor had computer B and I had computer A? And you say, well, I could increase my clock rate of the slower computer so that I could have an equal performance with B. If B is my competitor and I'm stuck with A and I can't change the CPI, well, what I could do is turn up the clock. So with that, we know that A is slower, so that the frequency of A would have to increase. Here we can say then that we want the CPI of A times the cycle time of A to equal the CPI of B times the cycle time of B. And let's draw this back. Remember what we had at the first. Well, we only have those two constituents, but remember, if we added number of instructions to this, the number of instructions would be the same on each of these, and so they would come out of the equation. So for that, we can plug this in. We've got 3.775 times the cycle time of A is equal to 2.52 times the cycle time of B. Remember, the cycle time of B was 0.556. I'm leaving the units out of here. And so the cycle time of A, to get them, when we solve that, we get 0.371 nanoseconds. But that's not what they ask us for. They asked for the clock rate. Well, the clock rate, the frequency is going to be 1 over this time. So the frequency of A is 1 over the cycle time of A, which is equal to 2.69 gigahertz. Okay, so that's our answer. And so does that make sense? Well, what did we say before? Well, A was at 2 gigahertz, and we saw that it got beat out by about 35%. Well, you can imagine you'd probably need to up the clock rate, and so now we see we up the clock rate. This is an increase in the clock rate by about 35%. If you take a look, we started at 2, we ended at 2.7. That's a 35% increase. Wait a minute. Here we needed a 35% increase. So if we were able to up the clock rate of A, then the performance of the two computers would be the same.